what I can do is I can recommend a very good which one do you want, or both? You want to know high level of both? And okay. This is probably going to be the fastest treatment of either Gaussian mixture models or Gaussian processes that I've done. So let's see. So is everyone comfortable with the Gaussian? Yeah, I'll assume that, otherwise it's going to take too long. Why is the Gaussian special? What is special about why is it an interesting function or distribution? In the frequency domain, it's a Gaussian, okay, but it was important even before that, right? Before people. Okay, those are properties of the Gaussian, but why? Yeah, okay, so one thing is you can take any distribution, draw samples from it, right? And if you average, so if you take uniform in any domain and or any function, you distribute this according to any function over any domain, and you look at the random variable, which is sum of xi, this will be distributed in the limit of large numbers as a Gaussian. That's the reason the Gaussian is very. Is there any other reason? Also, it's an exponential. So if you apply a derivative operator, it doesn't vanish for any derivative, which means it is almost can be considered infinitely smooth, right? So that's another reason. And it appears everywhere, right? Like if you solve the heat equation, you get an exponential. You get this, and you solve. Okay, so the exponential is a very important family. The Gaussian is a very special member of that family. Squared exponential. Now, so it is, and also it's easy to sample from. You can draw samples from a Gaussian and all that. So what happened was people started looking at applications where there were functions that were quite complicated. And they wanted to represent these functions. For example, a mesh, okay, or something else. And they didn't realize, or they didn't know how to store this function. One way to store it, just as with the mesh, is simply with the point values. But if you want to then interpolate and all that, it's messy. Secondly, you have to store all the points. So they wanted a simple approximation for this function. Now, if you want to sample from this function, it's not easy. So what they said was, oh, perhaps we can get a family of Gaussians and add these Gaussians to get this function, right? So what we're hoping is f of x is approximately equal to the sum of a number of Gaussians. And each Gaussian will be weighted by a different amount. You can see this Gaussian is weighted by a large weight. This is small. This is nothing but a decomposition, right? Like you're representing the function as a, it also can be seen as a projection. And you have this number of Gaussians. That's all. That's all a mixture of Gaussians is. And now if you want to sample from this mixture, you can, there are ways in which you randomly pick a Gaussian proportional to its volume, and you sample from that Gaussian. And so you can sample from it easily, and you can do many operations easy. So if you want to do a Fourier transform, you can simply take a Fourier transform of this, the sum, and you open it out in each of them. So a lot of operations are easy now because we represented it as a Gaussian. And we can do this in high dimensions and so on. I think that's all I'm going to say about mixture of Gaussians, because that should give you the general idea. Okay, so now let's look at a high dimensional. Remember that 2D Gaussian, and we have generated different samples, right? When we generate different samples, each of those samples we said had xi and yi. Now let's plot this slightly differently. Okay? Now if I plot it in this space where this line is x, the x coordinate of the points, this is y, then perhaps I can have this. So each of my samples I can now place like this, right? So the y-axis here in this plot, on this line it's the x-coordinate, on this line it's the y-coordinate. Is that clear? Okay. Now, if I go to 3D, what happens? I may have a z-coordinate, right? And so on. So I can go to any high dimensional space, right? So this could be the 4th dimension, 5th dimension, 6th dimension. So if I have a 6-dimensional Gaussian, every sample that I draw in that Gaussian can be represented in terms of points here, right? So if I take, for example, the first point, this is so the black point is the first. So let me change that from red, make it black. So all the black points here are the first sample. It is one sample, x1, y1, z1. Then the 4th dimension, 5th dimension, 6th dimension, right? You have a 6-dimensional sample here, which can be represented like that. And of course, I can think of this as being something like this, right? Now, if I do this, it's starting to look more and more like a function. Remember, that's one sample in this high-dimensional space. It's starting to look like a function. So as I increase the dimensionality, I get something like this. But remember, this is not the domain anymore. I'm just plotting all the coordinates of this Gaussian. Now, this is very interesting because this means that if I can sample in that high-dimensional Gaussian space, I can actually generate functions. I can generate a whole family of functions. Okay? What is it? So, for example, that is one sample. This is the second sample. This is the third sample, and so on. Remember, how do we get this? X-coordinate, Y-coordinate, Z-coordinate, 4th dimension, 5th dimension, 6th dimension. So it's just one sample, and you've just plotted each one across. The distance between these is fixed. Right? What is common to all of these? There's something common to all of these. What is that? Yeah? Yeah, these are all samples, but what is common to these samples? All these samples are drawn from the same Gaussian. Right? So we remember, we had a Gaussian, some high-dimensional Gaussian. We had 5 different samples. We took each of those samples. We took the x-coordinate of the sample, y-coordinate, so each dimension of that sample. And we did that for all the samples, right? And each of the samples now gives us a curve in this representation. And that, all these curves are random draws from the exact same Gaussian. And what defines a Gaussian? It's a mean and a covariance. Okay, yeah. Yeah, they're all IID. They're drawn from the same Gaussian. They're totally independent, right? So they are all independently drawn from the same distribution. So they are identically distributed, but they're also independent, okay? But the X and Y coordinates of these things are not independent. It's a good question. So if you look here, this sample is totally independent of this sample because they were all drawn independent. But Xi is not independent of Yi because Xi and Yi are related by the covariance of the Gaussian. Okay, if the Gaussian was like that, perfectly isotropic, circular contours, then Xi and Y are independent. But if the Gaussian is narrow like this and shaped here, for example, then Xi is almost linearly dependent on Yi, right? Yi is linearly dependent on Xi. So in this case, X and Y, the coordinates are correlated somehow. And not just somehow, we know exactly the covariance matrix of this Gaussian. And this Gaussian is known, we are sampling from it. But these 2 points are independent, which means in this space, the position of this with respect to this is correlated because it's the X coordinate and the Y coordinate. They are correlated by this, they are connected by that covariance matrix. But these 2 curves are independent. The red and the green curves are independent of the black and so on. Every curve is one sample, right? So this is an interesting view of Gaussian processes that I find very intuitive. Okay, apart from doing all the maths, it's always useful to keep in mind that these are independent, but within each curve, this covariance matrix determines the shape of the curve. Both the mean and the covariance determine the shape of the curve. So now if I want to change this family of curves, I simply modify sigma and I get a different family. Okay. Now imagine, okay, I'll try to wrap this up quickly. So imagine now that you are given your data, you are given some values. Okay. So let's say that you are given these samples for a function that you want to reconstruct. That's a nonlinear regression problem. There's some nonlinear function. You are given some sampled versions. So for example, it could be a field. It could be anything else. Okay, it could be a scattered field, for example. And now you're asking the question, what is the value of this function here? The old school way of doing, well, the simplest way of doing it would be to connect these all by linear segments, and you say the value of the function is. You could fit a polynomial, and to the nth degree, you will get some interpolant, right? You could fit piecewise Bezier curves. You could do all kinds of things, and people have done a lot of that. You could put kernels here and convolve, and you could get it, and so on. Since we're talking about Gaussian processes, what this means is we know that all these curves here must pass through this point. So we enforce that. We say that these samples all have, let's say this was the x coordinate, we are saying we know the x coordinate. Now if you go here, what it means is we know the x coordinate. And we have a 10-dimensional Gaussian. This will just be one plane, hyperplane in this 10D space, where x is equal to whatever you know. Then this distribution is a Gaussian. You slice the Gaussian along any hyperplane, you're going to get a Gaussian. So, axis-aligned hyperplane, you've sliced that, so you end up with a Gaussian, which means conditional on x being this, you are still left with a Gaussian process. There's a family of curves which can be drawn just like this, all of which pass through this point. That's the constraint now. all of these curves pass through this. Now your dimensionality has reduced by 1. If you have a 10D Gaussian, correct, and now you say one of the dimensions is fixed to be this, then you have a 9D Gaussian, and these, the covariance matrix tells you what 9D Gaussian these are all drawn from, right? So similarly, every point that is given to you narrows down the dimensionality of that space, but also narrows down what the family of functions can be. So if you constrain this now to pass through every single interpolant point, then you may get you can have any behavior in between. But at those points, it's going to intersect and so on. Right? So you'll get a family of such curves. And the more points you know in your original signal, the tighter and tighter these get. And between 2 points where you've been given the value, there is variation. So you can say there is a variance associated with this, which becomes 0. There is a variance associated with that, it becomes 0. There's a variance. So this black outline here is the variance. It's related to all our sampling things because now the reconstructed curve or the interpolated curve is a family instead of 1 point and is bounded by or is also known to have a certain variance between the sample points. So you know it is going to interpolate the point. And there is a version where it doesn't even interpolate the points. You can add noise so that it doesn't actually interpolate them. And the nice thing is you have this variance at points. Okay. And we saw this font manifold yesterday, right? In the font manifold, on the bottom, you had this figure where you have points and you had color coding of red and blue telling you how likely it is to be a font, a predetermined font. It was nothing but the variance of this. So when you fit a Gaussian process, what you're doing is actually giving all these as constraints and getting this family of curves whose mean is your interpolated curve. Remember now, because that mean is an interpolated curve, you can evaluate it at any point here. Okay, so the really nice thing about Gaussian processes is that it is not a parametric representation. Parametric representations have problems when it comes to certain dependence on data, and if the data is not great, and if it's nonlinear, then it's hard to fit. It is not a non-parametric method because non-parametric methods have their own thing is fully determined by the data, and you have to. And then traversing these families will be hard with a non-parametric representation. It is a semi-parametric method in the sense that depending on what these are, if you consider them parameters, you can actually get a parametric estimate of this mean anywhere in the middle. Because you're given this Gaussian family, you can estimate it. However, this fitting process is computationally expensive. I think it may be order n squared. I don't want to commit. So it's computationally expensive because it requires the matrix inversion when you fit and solve this. And so if you have a very large number of points where you want to estimate them or you're given these things, that matrix grows and it becomes complicated. And there are sparse methods to do this and so on. And I would recommend you watch a video lecture by David McKay on this. Very well done. It was a summer school many years ago. But it's perhaps the best lecture I have seen on this topic. David McKay, I think his name is. Let's see. It's MAC. So this video lecture is not. This is one of the best that I have seen, and there are many people who give very good explanations of this, but I would say this one appealed to me the most. Because he does this with a live demo. Have you seen this? He does it very well. Like he has R, he writes code in R, and then he fixes one by one these variables, and he'll show you what these functions look like. And he'll keep generating functions, so you'll see them oscillate. So it's a very visual thing, and then he'll explain the mathematics behind it. Okay, so I think that should, is that, do you have any specific questions about Gaussian process, or are you happy, something like that? And then you can use these to get latent variables and so on by, yeah, so we looked at some of this yesterday. I leave you to connect the dots. Okay, is there anything else that you would like me to cover? Let me see, is there something else in here that I didn't get to? Turn all this. Okay, so then I'll spend 5 minutes, because some of you asked me this thing. So how many of you are bachelor's, BTech students? 1, 2. Are you bachelor students or PhD students, right? So only 2 bachelor students. Again, how many of you are PhD students? Okay, quite a few of you. Okay. Okay, so I'll just tell you later maybe about the bachelor. So they were interested in how they could apply to a PhD and so on. So maybe we should discuss that offline. For the PhD students, obviously, there is this website, which is where most postdoc positions will be advertised. Okay, not just University of Edinburgh. I mean, for the UK, there is one site where you can apply. And I would say a lot of institutes, universities in the UK will post their ads there. And there are a lot of positions, so, you know, keep applying. So in addition to applying to great places here and in the US, also consider the UK, because there's some very good institutions there and there's some good labs. And obviously they also apply for, advertise for positions and so on. Okay, so now let's get to the competition part. So I've added it to your lab as lab 9. So change that to. So the goal is that we would like you to integrate some function here and write your program in such a way that we can replace this function with something else. Okay, and then we'll use the Metropolis-Hastings algorithm. You can use standard implementations of the algorithm if you want. If you feel motivated to implement it yourself, you know what the acceptance ratio should be. It's fairly simple. The key will be somehow you need to decide what this proposal distribution should be, right? In our case, it was G of X. That was dependent on the position. You can use a constant G of X. So what I'm trying to say is if you want to just solve the problem, it will probably take you about 15 minutes. You just have to generate, call the Metropolis-Hastings and give it some G of X, and your problem is solved. Okay. But that may not work well. You may need to tune G of X, for which you may need some intuition. And also, when every time you do these things, I would urge you, take the samples that it gives you, plot its histogram, plot f of x, and see if the histogram matches. Okay. So the problem with this is, can anyone see a problem straight away with f of x? It goes negative, right? You already ran into this issue before. So you can maybe do this. Should take care of that. or you can add any constant here, maybe 1.5. Then we add 1.1, just in case you get problems at 0 and so on. Okay? So now that's the function you want to integrate. Use Metropolis Hastings to sample it. And if you sample it with Metropolis Hastings, you should get many samples. You plot the histogram, it should match this. So what I would like you to do is plot the function, plot the histogram in your debug, and make sure they match. Okay. Then once you do that, calculate the integral, and then calculate the MSE. Plot the MSE for increasing n. Okay. In log, see what you get. Then replace your Metropolis Hastings samples with random samples. So this is simple Monte Carlo, this is Markov chain Monte Carlo. Compare the two and see whether it's worth doing Markov chain in this case. Maybe you can tweak your proposal distribution till you get something interesting. And then once you get that, explain why you chose that proposal distribution, why your intuition made you choose that, or why by repeated experiments you converged on that proposal distribution. So obviously these two are lower in terms of weights because marking, because you can just use anything. And I think what would be key is this. So what we'll do is, it's 12:11, and lunch is usually here only at 1. You can break into groups if you want, as long as you have an understanding on who will get the prize, because the prize is probably not something you can share unless you're very close to each other. So if you have that understanding, and I don't even know if they'll give you multiple certificates. So if you're happy that the other person in your group will get the certificate, or if you want an arrangement that one of you gets the prize and the other gets the certificate, that is all up to you. Then you're welcome to break into groups. Is that reasonable? Oh, if there's no certificate. Okay, can we not give a certificate saying this person won the contest or something? No? Okay, so in that case, then you really, okay. So the prize, I think they said they will give something. And if not a certificate, then I can write saying I taught this course and you won it for what it's worth. But you can put it on your CV and give me as a reference if you want. That's not a problem, even if I don't give you a certificate. Yeah, so we will have, how many of you? So how many of you are planning to work in groups? Can you just point to your group member if you're planning to work in groups? So that's one group there, one group there. Group, 3, group, individual. You want a group? So 3 of you. Want a group? 3 of you? Okay, so 1, 2, 3, 4, 5. So you have 5 groups. We can have 5-minute presentations from each group. It would be nice if all of you speak in the 5 minutes, not just one person. And so that means 25 minutes. And they want to close at 3:15. So I would say 10 to 3. Let's make it 2:45 to 3 so we have a buffer. So 2:45 is when, you don't need to make slides, but you need to be able to articulate these, right? Show these plots. And maybe I will do one thing. I will create a Google Doc, okay? And each of you can take one page, copy paste your plots there. If you feel you don't want to reveal your proposal distribution, don't type it there. You can come and when you present yourself, you can draw it or something like that. If you're happy to put your proposal distribution there, go ahead, that's fine. And if you put a proposal distribution, somebody uses exactly the same, whoever puts it first, obviously. So there's a trade-off there, right? Whether you want to put it on that. Yeah, and this is a very real problem because in research you're faced with the same thing, right? You publish something, you come up with something, you may want to put it out as a tech report, as an archive or something. There's always the chance that people start thinking along those lines if it's a brand new thread because of your tech report, and they may publish. It has happened to me as well in the past that people have published that. And the other work that Fredo put out the tech report, he put out the tech report maybe 2 years before our publication, but our publication was published first. So it all depends. So I'll let you make that decision as well as a rehearsal. If you want to put everything up on that page, go ahead. Other thing is okay, so I'll create that. And then when we do the presentations, at least it'll just be one document. We can go through it easily without slides and all that stuff. And you can just talk about it. Is that clear? Any questions? Any questions about this question? So I'll be around, and there will probably be a few things that are a bit ambiguous about this problem. One or two intentionally, and probably many unintentionally. So if you have any clarifications at any point during this thing, you can always ask me. Okay? So yeah, other than that, I hope you enjoyed the lectures, and it wasn't too boring or too what you call mathematical in terms of this real. I know that we don't look at real spaces so much, or continuous spaces so much. We look mostly discrete. But I think most applications, especially in computer science, is a very important thing. So for example, the mesh community. So this guy, Matthew DeBron from Caltech, he early on, so have you read his course notes on, what is that, discrete operators, discrete forms. So have you read that? It's a must. Anyone who does geometry processing, I would say absolutely needs to do this. Okay, there is a course by him on discrete differential forms. Maybe somebody else is doing this now. No, what is it? Discrete forms. Yeah, something like that. Yeah, something like this, right? So this is now given by Keenan Crane. And there are SIGGRAPH notes on this. So is this the SIGGRAPH notes? Yes. This one says 13, but I think there've been versions after this. Okay, I think Matthew and Peter Schroeder started doing this long ago, and it has developed. And that is a key. That's a great example of how they showed that even though your problem domain may look like it's discrete, there is an underlying continuous problem formulation, and there is a jump from the continuous to the discrete formulations. And this jump, which people trivialize, sometimes needs to be considered. So all of this stuff, what they do is they rigorously show what you need to do in the discrete space. Okay? And I think a lot of this came about because Matthew always thought about this continuous discrete stuff. I remember even like 2001, 2 or something when I met, he was talking about all this continuous space, and he was complaining that at graphics, everybody only looks at this after it comes into the discrete domain, and that there's a lot of sort of subtle things that do matter in that jump. So yeah, so what I'm trying to say is I think a lot of the sampling that I showed you is in the continuous space, and you may think, oh, I have a discrete problem, but I think it's worth looking at A, what the continuous formulation of your problem is, and B, also alternative spaces. So even though your actual problem may be dealing with something discrete, there may be alternative spaces like this latent space or something else where suddenly you have a continuous space which you can explore or sample or even take expectations over. And I think that's one of the reasons I always like to present the sampling course in the continuous domain. Okay, so that's about a summary. Now I'll just let you get to your projects. If you have any questions, yeah, feel free to ask, and then we'll close, I think, at 3:15. So your projects, or maybe I should put that there. Due at 2:45 p.m. Just to be precise, or well, in case some of you have other ideas. So.